Let's talk about LCR circuits, inductive, capacitive, and resistive circuits. This diagram shows how our circuit is laid out. We have a motor, a capacitor, and a resistor all wired in series. A three-way switch controls whether the circuit goes through the motor or around it, and a second three-way switch controls whether the circuit goes through the capacitor or around it. The circuit always goes through the resistor.
Let's talk about the setup for this little experiment for just a second. This is a series circuit with an inductive load, the motor you see on the left, a capacitive load, the capacitor you see in the center, and a resistive load, the green power resistor you see on the right. So all of these things are in series with each other, and I have little meters to monitor the voltage and the current and the power factor of each individual load as well as the entire circuit. I have three-way switches to control whether the current goes through the motor or around it, and also whether the current goes through the capacitor or around it. Let's see exactly how this works. So first, I have the oscilloscope monitoring the voltage coming into the circuit on channel 1, the probe you see right here. And then this three-way switch controls whether voltage goes through the motor or around the motor to the next switch. And then this switch controls whether the current goes through the capacitor or around the capacitor to the resistor. And the resistor will always be in the circuit. And then you see I have channel 2 of the oscilloscope checking the voltage across the resistor. Why do I want to check the voltage across the resistor? Well, because the current will always be in phase with the voltage across a resistive load. So by checking the voltage across the resistor, I can also see the phasing of the current in the circuit, and therefore we can see how the inductive and capacitive reactance affect the current versus the overall voltage of the circuit.
Let's turn the circuit on.
Here I have a circuit with an inductive load, the little motor on the left, a capacitive load, the capacitor in the middle, and a resistive load, the green power resistor on the right, all in series and all operating at the same time. The circuit is fed with 136 volts AC. The motor is receiving 105 volts. The capacitor, almost 97 volts. And the resistor, 86 volts. Now let's see what happens if I take the motor out of the circuit. And this is a three-way switch, so it's basically going to just bypass the motor. So now I have a circuit with more capacitance than inductance, and the current shifts ahead of the voltage. Put the motor back in, and take the capacitor out. Now the circuit has more inductance than capacitance, so the current lags the voltage. Take both of them out. Now we only have resistance, and you see the current and the voltage are exactly in phase. Now, when we've got only resistance, all the voltage is going to my resistor. So here's the voltage coming in, monitoring the current and voltage coming in. And here's the voltage across the resistor. The other thing you notice is the power factor is 1. That's because the current is always in phase with the voltage across the resistive load. So the whole reason we're checking the voltage across the resistor right here and comparing it to the voltage coming in right here is so we can see the phasing of the voltage versus the current. The dark blue line is the voltage across the resistor, and the light blue line is the voltage going into the circuit. And when I add inductive reactance by turning the motor back into the circuit, the voltage across the resistor now peaks behind the voltage to the overall circuit. That indicates that the circuit current lags the circuit voltage. And now you see the motor's getting 89 volts, and it has a power factor of just barely over a half. The resistor, meanwhile, still has a power factor of 1. The power factor on the overall circuit, though, has gone down because now we have this low power factor device included in the circuit. Now let's take the motor back out and bring the capacitor in. And now the current is peaking before the voltage. If we look at the capacitor voltage, it's getting 101, and the power factor is terrible. And the resistor now is almost 90 volts. The power factor is still of 1. The power factor for the overall circuit has gone down to 0.6. Now what happens if I bring the motor back in while leaving the capacitor in the circuit? So then the inductive reactance and the capacitive reactance offset each other, and we have a resonant circuit. And now the power factor for the overall circuit is almost 1. My resonance is not exact. You see the power factor through the resistor is still 1. Power factor through the capacitor is still terrible. And the power factor through the motor is still about half. So let's go through this one more time. With the resistive circuit, all the voltage is being dropped across the resistor. Power factor is 1 on the circuit and on the resistor. And you see the current is exactly in phase with the voltage. If we add inductive reactance by bringing the motor back into the circuit, now the current lags the voltage. The power factor for the little fan is about 0.5, and it's receiving about 90 volts. Power factor for the resistor is still 1, but the voltage it's getting has dropped to around 67, and you see the voltage coming into the circuit still pretty much the same. Now I'm going to take the motor back out and bring the capacitor in, and now you see the current leads the voltage. The capacitor is getting 101 volts, while the resistor is around 90. The resistor still has a power factor of 1, and the capacitor has a terrible power factor. And the overall power factor of the circuit is 0.6. But magically, if I have both capacitance and inductance, and if they're at the right levels to offset each other, then the current and the voltage are back in phase. My circuit power factor is back to almost 1, even though the power factor for the individual devices has not really changed.
If you have paid attention, you've probably noticed that the sum of the voltages of the individual components add up to more than the original applied voltage. This does not mean that magically the circuit is creating voltage, but where does the extra voltage come from? The AC current flowing through the motor is constantly changing because it is an AC current. This creates a constantly changing magnetic field, which generates a new voltage, and this voltage is called a reactive voltage. It is, in fact, inductive reactance. This inductive reactance opposes changes in current. While magnetic devices react to changes in current, Capacitors react to changes in voltage by alternately storing and then releasing electrical energy. This creates a reactive voltage across the capacitor. The voltage measured across the capacitor is entirely reactive voltage. You may recall that when the motor was in the circuit, current lagged voltage, and when the capacitor was in the circuit, current led voltage. Then, when we used both of them in the circuit at the same time, they offset each other. This offsetting effect reduces the overall impedance of the circuit. Voltage across any device in a series AC circuit is equal to the current times the impedance of that device. When the impedance goes down, the current goes up. So, reducing the impedance by having the offsetting inductive reactance and capacitive reactance increases current, which increases the voltages across every device in the circuit. Now, while these voltages might appear to add up to more than the applied voltage, because they're out of phase with each other, they cancel each other out instead of adding up. Hi, this is Carter Stanfield, co-author of Fundamentals of HVACR. I hope you enjoyed this presentation. If you did, please consider buying my book. You can find it online at Fundamentals of HVACR, 4th edition, published by Pearson. Authors Carter Stanfield and David Skays.